Hi everyone, today I'm going to introduce you to the use of the Darling model. So in case your school have a set or two of it, then I think knowing how to use it will be an asset to the teaching of organic chemistry, or I mean in general related to conformational analysis or even the shapes of molecules. Okay, so I'm just going to move forward. So for the Darling model, it comes in two forms. It can be either a packet form. So a packet form will look like this. So this is the cheaper version. So if you Google www.darlingmodel.com or something along those lines, then you should have a choice of between either the packet form or the box form. Yeah, so my advice is if you want to get for your own use or for use in school, then and you want to order many copies or packages for your students, then I think it's a lot cheaper to get the packet form. The box form is a little bit more bulky and it costs I think 2 or 3 times more. So I think better check out the price before you purchase it. Yeah. So it comes in a set like this. So I think it's written as Darling model, and then inside the pack you have various instructions. So you have this pack here that tells you how to assemble. Actually, they do teach how to assemble, and in fact, within the pack, you can treat some of these things like a teaching resources as well. So they will teach you how to assemble them and then how to look at the necessary projections. Yep. So of course, if you have the time, you can look through them. But I think for today's video, the main thing is not about going through the exact details, but about simple usage. Yeah, you know, the kind of no frills way of use it even before you read the details. Okay, so I will first by showing you how does the Darling model work. Yeah, so it comes in different colors. So you can so they are like the black color, so something like this, and then it also comes in red, which looks something like this. Yep. And then you also have a gray color. So a gray color sometimes some of them looks like this. So I think it's kind of idiot proof to know that this would mean or kind of represent a double bond, and then this is the gray one. Yeah, so for those of you who are very confused at the beginning regarding what they actually are, right, they actually represent different atoms. So this particular book will tell you what each of the color represent, but today again we're not going to that. I think the focus is on what exactly is the black representing. So the black represents carbon. Yeah, so you can see that it takes on a very interesting shape. It's like a inverted okay, I mean it's like a V shape, okay, slanted bands. Okay, what you're going to do is you can clip both together like this. So so you can see that there's a bit of a hole over here. Yeah, so your job is to clip both holes together. Okay, but just make sure that when you clip them together, right, you do not just put them like this, because if you put them just like this, you realize that it's very loose. You can just take out quite easily. Yeah, so what you should do is you put them together and then you push it in all the way until you hear a click. Okay, so like this, just push in all the way. Yeah, you hear the click. If you want to release it, please do not forcefully release it, because if not, you will spoil the model. So what you can do is you can simply use your 2 fingers, and then you give it a gentle tap like this. So I'm going to give it a gentle tap. So I'm going to push it here, and then I use another hand to just give it a little bit of push, and slowly it will be released like this. Okay, so again, let me show you. These two pieces together come clipped. Yeah, so the newer model you can hear a clip. The older ones, I don't think you'll hear the clip. Okay, and then after that, to release, please do not forcefully release them. Just give it a gentle tap, and then it can be released like this. Okay, yeah, so you do the same for the red one. Yeah, so the red one actually represent oxygen. Yeah, and then after you have done it, right, you realize that it looks like it's actually a tetrahedral shaped. I think you can tell from the model over here. So it has a tetrahedral geometry. Yeah. So how do you actually see that it's a tetrahedral geometry? Well, I mean, if I use my palm, okay, I'm going to move to the back. If I use my palm to represent the screen, then I put my these two bonds, okay, which is on the surface or on the plane of the palm, right? Then you realize that this group is projecting towards you, okay, and the other group is projecting away from you. Okay, can you tell that? Yeah. Okay, so this is the reason why the Darling model is actually a good model, because of the way it's being designed. Again, this is definitely not a sponsored video, but a video focusing on how to use it for teaching and learning purposes. Okay, then you'll be wondering, after I've made this, what's the use? Okay, so the use is you can actually join them together. So I'm going to make another tetrahedral shape. Okay, I'm going to put them together. Okay, and then I'm going to go to the back to show you what you can do with it. Okay, so what you can do is this two. Okay, you realize that there's actually a hole over here, and then there's a little bit of so there are two ends. One is a hole. Okay, so the other one is a little tube here for you to connect to this hole. Okay, so what you can do is this hole and then this clip. Okay, so you can just put them together. Just insert it with a bit of force. Okay, so you can just put them together like this. Okay, and then this can actually show you that a single bond, in this case a sigma bond, has free bond rotation. Okay, so free bond rotation like this. Yeah, so we can then demonstrate to the students how this free bond rotation works. So I think this is a very good way of showing the students how flexible a single bond is. Okay, as compared to a double bond. So now I'm going to show you a double bond. So you have a CC double bond over here. Okay, then I'm going to illustrate with ethene over here. So you see that compared to ethane, right? Compared to ethane, where there's free bond rotation like this, for ethene, you can't rotate. Yeah, by virtue of the pi bond. But of course, you can tell that it's a bit of a cheat here, because this is a model where, of course, you see a double bond here, you can tell the restricted bond rotation. Yeah, but that's precisely the point. Because of the design of the model, right, it gives you an indication of the rigidness of a CC double bond as compared to just a single bond. Yeah, but of course, when you are using it for teaching and learning purposes, it's not just about showing free rotation or rigidness. Okay, you can also use it to show to do conformational analysis. So I'm going to go to the back. Okay, so maybe before that, I'm going to show you some other things you can have. So yeah, over here you have some spheres. So if you are interested, the sphere actually represent atom as well. Yeah, so I'm going to just open this up a bit. Okay, so white represent hydrogen and red represents oxygen. So I'm just going to indicate the position first. Okay, so I'm just going to put in the hydrogen over here. Okay, and another hydrogen over here. Yeah, this is just for fun. Okay, again, I'm putting the hydrogen in is just for illustrative purposes, because technically I should be putting hydrogen on all the carbon, I mean all the N. Okay, but I'm not going to do that for now. Okay, the reason is I'm going to show you how it can be done to illustrate conformational analysis. Okay, now I think first of all, right, when we teach especially organic chem, we are normally interested in teaching especially for H3 conformational analysis between two important conformation. Okay, so you have an eclipse conformation. Okay, over here, can you see that now these two groups are facing each other, and of course these two groups and these two groups. And then after that, we are going to normally show the students, either using computer modeling or you let them play with the model, how you can actually rotate this to give you the eclipse conformation. Sorry, staggered conformation. Yeah. Okay, and then I'm going to rotate more again, and then you get back eclipse. Okay, and then I'm going to rotate again to give you another staggered, and then rotate again to give an eclipse. Okay, and then rotate again, finally give you another eclipse conformation. Okay, so I've missed out the other staggered conformation, which is like this. Okay, so this is the other staggered, and then eclipse. Okay, right, so let's try again. So from here I rotate 60 degrees. Okay, so this is staggered, and then eclipse. Okay, and then staggered, eclipse. Okay, and then staggered, and then eclipse. Okay, Then, of course, when you're using this for teaching, you can also ask the students to visualize how this can be drawn on the board. I'm going to insert two more different colored balls into this model so that you can see how conformational analysis could be done and then how it can be used for teaching and learning purposes. Yeah, so you notice that now I'm purposely going to leave it as a eclipse conformation so that later I think it's easier for us to draw as well. Okay, so I think first of all, I'm just going to put the two green sphere on one side. Okay, and then the two red sphere on the other side. Okay, so as to give you a meso compound. So again, one of the advantage of using this is also how you can easily teach the teachers, and of course the students, what exactly is a meso compound, because if you create the same model out as a mirror image, you realize that they are entirely superimposable. Okay, so that's something which you can use it you can use in an expert manner Darling model, and how Darling model can help you in your teaching and learning. Okay, so I'm going to illustrate this molecule on the board right now. Okay, so over here you can see that this is indeed eclipse conformation, something like this. Okay, so I'm just going to position it properly. Okay, yeah, like this. So you can see that now the two OH is knocking onto each other. Okay, and then the hydrogen is to the left, and then the chlorine is to the right. Okay, then you can also ask the students to try to draw this out. Okay, so I'm just going to try to draw this out by writing this. Okay, OH and then H and then Cl. Okay, then of course when you are trying to teach the students, it's also useful to point them in the correct direction, where they should position it in such a way that they are not able to see the atom at the back, the carbon atom at the back. But of course, it's not so straightforward using the camera like this. Okay, but something like this. Okay, so can't really see. Yeah, so this is the eclipse conformation which we want them to draw. But of course, when they draw it, they can't be drawing it in such a perfect manner. So it will probably look something like this, something like this, and something like this. Okay, and then later on, what you can normally tell the students to try is you can ask them to try to do a bond rotation 60 degrees clockwise. So over here, I'll do a 60 degrees clockwise rotation. So I'm just going to put my hand here to just rotate it 60 degrees like this. Okay, so I'm going to get a staggered conformation. Okay, so we're going to try to draw this to the right hand side. Okay, so again, when you ask the students to draw, it can be quite flexible. Yep. So it can look like this. Okay, and then after that, the OH will be here, and then the Cl and the H. Okay. Yeah. Then after that, we can continue to illustrate the use of this by asking the students to keep drawing. So I think, okay, sorry, it's the other way around. Oops. Now I don't know where my model is pointing. Okay, something like this. Okay. Yeah. So this is what I had earlier on, and then again, oops, sorry. Okay, so this should be the one. Okay, so this is the one on the board, the right hand side. Okay, so I'm going to rotate again, like this. So this is another eclipse conformation. Okay, you can also ask the students to draw this, and then after that can draw this, can draw this. Okay, and then this, and finally back to our original eclipse conformation. So there are a total of 6 conformations to be drawn. Okay, like this. Okay, so my apologies that I cannot hold the model in position properly. Okay, yeah, but you get the gist of it. Yeah, so besides conformation analysis, right? Conformation analysis, what else can we do? You can do chair conformation as well, or you can try to build a chair and then let the students feel the rigidity. Okay, maybe a 4-membered ring versus a 5-membered ring and versus a 6-membered ring. Okay, which I'm going to illustrate to you right now. Okay, so that's why the Darling model is brilliant in this aspect, because it can gives you the kind of a feel I think as a student, because I had the experience as a graduate student using the Darling model in teaching and of course in learning confirmation. Okay, so how do we build a chair? Well, I mean, you just build it, right? So you need four, or rather you need 6 sp3 hybridized carbon. So you need 6 of this. Okay, so you just build them together. So I'm going to add one and then another one over here. Okay, but of course before that we try to build a 4-membered ring, and then you get the students to feel the rigidity. Okay, so you can see that now I'm forcing them together. Can you see the model bending towards each other? Okay, can you see that it's like very unstable, and then it's going to spoil my bond anytime? Yes. So again, advice is try to get the students not to build this, but just to feel the rigidity. Okay, yeah. 5-membered ring, I think it's fine. I think 5-membered ring is still not so not so rigid, and it will probably not spoil your model, so we can try it. So let's try, yeah, something like this. Yeah, of course when the students build it, they will be able to feel that it's not as flexible as a 6-membered ring, okay, as they like to be. Okay, so again, I'm going to open it up, and then let's try to do a 6-membered ring. Okay, like this. Yep, so we have a 6-membered ring over here. Yeah, so again, I think for the purpose of teaching and learning, the easiest way is just to get them to build first, and then just to randomly play around like this. Okay, so randomly let them flex, so that they can feel whether this is a flexible chair or not a very flexible chair. Okay, you can see that this chair is quite flexible. I can easily do the flipping between the boats and the chair conformation like this. Okay, so that means that this model, I mean, it's still pretty new now, because when the model is quite old, then you might not be able to flex so easily. Okay, yeah. So after you have built it, right, then it's time for teaching and learning again. So what can we do? I think the first thing we can do is we will try to ask the students to position it in such a way that they can see the chair conformation. Okay, so from here, we can do a bit of rotation, maybe like this. Okay, I hope this is clear enough. Like, oh, sorry, just, oops, I need to twist it a little bit more. Sorry, bring it a little bit closer. Okay, like, oh yeah, like this. Okay, yeah, I think you can see the chair conformation quite well from here. Okay, so this is the chair conformation we're talking about. Okay, yeah, so for teaching and learning purposes, one way is really to indicate the axial and equatorial position for the students. Again, just for teaching and learning purposes. So what I'll do now is I think I can use the sphere, because I do have a number of them. So I'm going to use the red one. So I'm going to take out all the red one, just to showcase to you the axial equatorial position, so that when we try to use this with the students, it's easier. Okay, yep. So I'm going to I think the first thing I'm going to do is I'm just going to put in this particular sphere in all the axial positions. So here, 1, okay, and then 2 over here. Okay, sorry, that's taking a bit of time, because I don't have I don't make models available. Okay, I don't pre-prepare the model, so it does take a bit of time for me to insert. If you want, you can fast forward. Yep, and then we have this over here. Okay, and then another one below. Okay, and then yep, the final one over here. Okay, excellent. It's like that over here. Yep. Okay, so okay, I will try to give you the views. Okay, like this. Yeah. Okay, so this is the chair conformation we're talking about. Okay, you can see that all the OH group are in the axial position. I don't know if this is obvious to you. Yeah, and then all this without any color. Okay, there should be, I should put white hydrogen. Let me see if I have enough hydrogens. Okay, because if I have enough, I think it's easier for visualization purposes. Okay, yes, I do have enough hydrogen, so I will do that. Yep. so that you can see when you do your ring flips, it can be done quite easily. And then if you have large groups, you can use it to incorporate the 1-3 diaxial interactions. Okay, but I think it's okay. We'll just ignore that for today. Okay, so now I'm just going to put in the groups. Okay, yeah. Okay, the groups here, and then over here, and then here. Okay, yeah, I think they're in. Okay, so now I think this is perfect. So we try to sketch this. The chair conformation. Let me try to put in a nice position so you can see. Okay, like this. Yeah, like this. Okay. Okay, so right now you can see that all the red sphere or all the OH group are in the axial position, pointing either up or down, and then all the hydrogen are in the equatorial position. Okay, so this equatorial position, it's kind of like pointing up as well, but it's not really up. Okay, it's like pointing in a slanted direction, and the other edge at the back is pointing away. Okay, yeah. So at this point in time, it will be good to actually ask the students to do and to illustrate this particular diagram, so that you, at least in teaching and learning purposes, it is clear that you are able to showcase how ring flip occurs. Okay, so later I'm going to do a ring flip. Okay, so right now I'm going to erase this particular Newman projection. Okay, and then I'm going to draw in the chair conformation. Okay, so in this case, I'm going to show this particular perspective, so it will look like this. Okay, and then the OH group is pointing down, up, down, up, down, and then up. Okay, yep. And then the hydrogen, which I'm going to use another color, okay, will be pointing like this. Okay, and then like this, like this, like this, like this, and like this. Okay, yep. So I'm just going to show you again, compare against the model, okay, to see whether it's exactly the same as the one I've drawn on the whiteboard. Okay, so I think you can tell that it's the same, even in terms of the positioning of the equatorial groups. Yeah, so remember that I have an earlier video for the students saying that how do you remember the position, particularly of this O, this H, and this H? Okay, you can view this as a like a W shaped, like this, and then you can view this as a M. Okay, like this. Okay, so if you are able to remember it, I think it's actually easier for you to predict the position. But if you have drawn it wrongly, I don't think it's a big issue. I don't think so, but maybe you know, the drawing may not look so nice. Okay, but what is more important now is I'm going to do a ring flip, because that is really the purpose of this particular video, and of course in helping every one of us in teaching and learning. Okay, so doing ring, what does doing ring flip means? Doing ring flip means that I'm going to flip this group down, and then the one at the back upwards. Okay, notice that when I do a ring flip, whatever group that is in the axial position will now be found in the equatorial position. Okay, so I'm going to do it now. Can you see that? Okay, now can you see that the hydrogens are all in the axial position? Okay, so maybe I turn it in such a way that you can see it. Can you see now? All the hydrogen are now in the axial position. So if I do a ring flip again, then the hydrogen is back into the equatorial position. Can you see that? But at any one point in time, you notice that when I do a ring flip, it doesn't change the direction where the OH and the H are pointing. So if this H is pointing up and this H is pointing down, doing a ring flip, right, does not change it. Can you see? Yeah, this H is still pointing up, and sorry, this OH is still pointing up, and this OH is still pointing downwards. Can you see that? Yeah, I think it's quite clear. Okay, and then this H is pointing down, right? this H is pointing up, right? So if I do a ring flip, okay, can you see that this H is still pointing up? The one at the back, sorry, the one at the back is over here, still pointing up, and then this H is still pointing down. So a ring flip doesn't change the configuration of the chiral center in that sense. Yeah, yeah. So do not be, I mean, in this molecule, of course, we have all the groups the same, but I'm saying that in the instances where all the groups, some of the groups are the same, some of the groups are different, then please do not artificially change the nature of the groups. Okay, so I think now the board is a bit messy, but I'm just going to show you after I do the ring flip, right, how do I actually draw the product? Okay, so you can of course draw it directly if you want, okay, but for complete sake, for the sake of completion, I'm just going to show you how it can be drawn. So when I do a ring flip like this, you'll notice that now this H is pointing up, right, and this OH is pointing down. Okay, so if I'm good, so one good practice, I think one good practice, even whether is it for teaching purposes or for students learning, is to number the carbon. Okay, so I'm going to illustrate this by doing some numbering. Okay, as this model is a bit, I mean, this diagram is a bit messy, I'm just going to change it so that just going to redraw it again so that you can tell. Okay, so right now going to use the black marker. Okay, so again, this is the chair conformation we started off with. OH, OH. Okay, and then we have the H pointing here, here. Okay, and then now we can try to number the carbon. It's really up to you how you number it. Do 1, 2, 3, 4, 5, 6. Okay, then now we'll do a ring flip. Okay, so we'll do a ring flip. You'll notice that this equilibrium arrow, right, it's leaning towards the right hand side. For a reason which I think in the course of our studies, you will learn something called 1,3 diaxial interaction. That means that the bulky groups, okay, if they are in a 1,3 position, they will have what we call significant steric repulsion. So normally we represent steric repulsion with this symbol. Okay, it goes like this and then like this. Yeah, it's like two semi-crescent crisscross each other. Okay, so this is what we call 1,3 diaxial interaction. So it's not favorable, so it will tend to perform a ring flip to a conformation which is more stable. Yeah, and then when we try to draw the chair, again, because this is being flipped upwards and this part is being flipped downwards. Okay, so it will look like this. Okay, like this. Okay, so if you have trouble doing it, I think it's good to number the carbon first so that you can track it. Okay, and then of course carbon number 1, OH, remember, is pointing downwards. Okay, so you have to point downwards. Okay, and then we do the same. So down, and then up, and then down, up, down, and then up again. You notice that all the OHs are in the equatorial position. Okay, and then of course now all the H are in the axial position. Okay, so what doesn't change is the direction where the groups are pointing. So that's what we are trying to say. OH is still pointing up, OH is still pointing up over here. OH is pointing down at carbon number 1, and OH is pointing down at carbon number 1. So nothing has changed. Okay, so yeah, so with this, I think when the students experience the direct usage, it's actually easier for them to see how the Darling model can help them to better learn about ring flipping. Okay, so with that, I've come to the end of the video showing or giving you an introduction on the Darling model and how to actually construct a tetrahedrocarbon from scratch, and then from there how to use conformational analysis on ethane, and then how do we actually translate that into a chair conformation and doing ring flipping. Yeah, so these are the sort of the most basic thing which you can use with Darling model. Of course, Darling model is not simply restricted to doing chair. As you have gone, if you have gone through the whole booklets, you can see that it actually can do a lot of wonderful things, lah. Like I mean, back then in the old pharmaceutical chemistry syllabus, you can use it to do Fisher projections. Okay, so I think it's extremely good in trying to teach Fisher projection. You can also use it to show the planarity of the benzene ring. Yeah, so there are a lot of things which you can do for or using the Darling model. So yeah, so I mean, this is just a very basic introduction on how to use it. If you could do study this, and then maybe we can do collaborate in the future to produce some excellent videos on how to use the Darling model for teaching and learning purposes. Yeah. So yeah, for the students watching it, I hope you also benefit from how you can use the model in your learning of conformations and how to actually translate whatever you're seeing in the model to the drawing. Okay, so with that, I thank you for listening to the videos, and I do hope to produce more of such models, I mean videos related to the Darling models in the future. All right.